We'll start now then. Hello everyone. Welcome to SVD Encore for Team Edge. We'll start off by giving a quick overview of our project and a summary of the progress that we have made over the semester. And then we'll move on to our planned demonstrations. So in our project, we are trying to create realistic traffic scenarios inside a simulator. And this can serve as a test bench for software stack of self-driving cars. And for this, we have identified 4 major subsystems: data capture, data processing, behavior model, and simulation. The idea is that we collect realistic data, extract relevant information using the data processing subsystem. This is then used to train a behavior model, and this custom trained model is used to control vehicles inside a simulator. In addition to capturing video streams using our own hardware, we have identified some other sources of realistic data. One such source is open data sets like new scenes, Argoverse, etc. And other is driving inside a simulator manually using a steering wheel. And these data sets would be pre-annotated. So for such data, we can skip the data processing part. And so this is how the relationship will look like in those cases. And we will now look at the progress made in each of the subsystems. For data capture, we have managed to convert nuisance dataset to the format required by behavior model. The video on the left shows the front cam view of the ego vehicle and the converted format of the same data. And we have also interfaced a steering wheel system with Carla and used it to collect data in the required format. For data processing, we have worked on detection and tracking in bird's eye view. We had 2 demos last week pertaining to this subsystem, but this time we will show only one of them, which is basically an integrated form of both detection and tracking. For our behavior model, we have used something called learning by cheating. We have implemented it as a baseline behavior model, and we plan on improving it in the following semester. And in our simulation subsystem, we are running multiple LBC agents inside the simulator. So our plan for the semester was to build the entire pipeline from data capture to simulation, and we have done that. This will basically give us enough time in fall to improve on the behavior model part of it. In today's demonstrations, so we had these 3 demos in our last week's presentation. Of that, as I mentioned before, we are not going to show demo 1 today. Instead, demo 2 already has the detection component in it. So we will go into details of demo 2 and demo 3. Next, Tarang can take over.
Yeah, so going on from that, last time in demo 2, we had pre-recorded scenarios. So we are extending that this time. And another feedback that we received on the SVD were additional details on edge cases and failure cases and a summary of all the statistics in general. So I will just summarize the edge cases of the demo 1 that we are not explicitly showing. In the detection model, one of the major failure cases is far away cars. They aren't being detected consistently. In the current example, current image, if you see over here, there is a car right now, but in the next frame it goes away. So that is one of the issues. Currently, it is not a major pain point as such because we are trying to keep a fixed region of interest at every intersection. So if when we have multiple cameras capturing the scene, we might get that car in another intersections camera. And yeah, so another failure case or something that we have to take care of is going to the mapping this to the real world. So we initially started using a model which was pre-trained on the COCO dataset, which contains cars in a variety of orientations and poses. That was working pretty well, but we feel that when we transform to the real world, we might need to do some additional level of annotation and fine-tune the model further to make it as good as this one. Going on to the demo 1. we will be capturing data from a live intersection this time. Last time we had our data capture process was slow. So we've optimized it to capture 30 seconds of video in around 1 minute of real time right now. Previously, it would take like 10 to 15 minutes. So we will now, like, we can just select a camera, so these are a few sample positions of the camera. These are located in these positions. I think this map is what we saw last time as well. So if anyone can suggest a camera number, I can start mounting a camera there.
About 62.
Sure. So I will, yeah. So over here, I'm just enabling 62 in the code and start running it. So this part is initializing the environment, spawning the cameras, and spawning the agents.
Sir, can you make sure Carla server is running?
Yeah,
Was it running before and we need to kill the video editor as well?
it seems there is an issue with traffic light 62. Can I try some other light if possible?
Yeah, just
Why not do 54 if 62 is a problem?
Yeah, just do another.
Okay, I think I know the issue.
I think why don't you just kill the server once?
Yeah. This apparently was a different map. I will try with 62 as only, which was our initial choice. Really sorry for the delay. So the map was different. So the mounting, we were trying to mount it at 62 and we didn't have 62. So yeah, we mounted the camera here. We applied the transform or the rotations that are needed for the location at this point. And the agents or the cars that we see, including the people, are randomly spawned. And they've been assigned random goals. So they're running the default autopilot behavior within the Carla system. And the boxes that we see are the ground truth that Carla provides us with. So we are storing these ground truth data and the raw video separately, which gives us the ability to also validate what we are detecting or validate our trajectories as well. This video eventually will be put into the pipeline, which we will see later, which we will see next, and have our both bird's eye view trajectory would be compared with the ground truth trajectory that Carla gives us. So in terms of the speed, we are almost there.
Tarang, I have a quick question.
Yes.
What we just saw, there was a car that came from the right side. So the cars on the left side, they're all stopped. And then there was a car that came much later from the right side and went. Was it a light there? It's a conformed to a light, I guess, that I missed probably.
Yeah. So I think the turns are available to that car, so that must have come in from there. I think we can see the video while running the next part of the demo.
It just didn't seem, it didn't make sense from a from a traffic
So
standpoint?
there is a traffic light, and we are capturing everything at an intersection, and all the agents are reacting to the traffic light.
Okay, I was just wondering because the other side, the side that's supposed to go straight, was waiting for a while.
Yeah, that's only because of the traffic lights. Like it probably was red for them.
Okay.
Yeah, I
Yeah.
guess like there are some traffic light semantics in Carla which are a bit. So the turns are available on the red light as well. So we are saving this file in a file called demo traffic light. So I will just change this to 62 so that the same video is being used. Now Harsh can take over with the next part of the demonstration.
Yeah, I'll run this. So now on the capture data, we'll run the detection and tracking. So yes, so hopefully we can see that scenario which is been mentioned. So so the capture data we pass through a detection algorithm, and then that goes through sort. So on the left, with the window name detection, you see sort's output, and the IDs are from sort. So then we have another tracker in the bird's eye view, which is on the right. So we transform the bottom center of the bounding boxes of the vehicles, like a point near to the bottom center. So somewhere around here for vehicle 2, if you can see my cursor. So we transform this to the bird's eye view and select. So this here you see this vehicle. And we're tracking the vehicles in the pixel space in the bird's eye view. So the reason we had another tracker was because sort was giving wrong associations and was like switching IDs constantly. So we employed another tracker in the bird's eye view. This tracker, we have set the threshold to be like 20 pixels in the bird's eye view, which corresponds to being around like 2 meters. And on that threshold, we are getting these tracker metrics, which Morte comes out to be 95 and Morte is coming out to be 67. So this data, like we haven't tested on this data, we are testing it right now only. So these numbers are, we are also seeing it right now, the first time. Yes, also this black polygon that you see on the right tracking, the tracking window is a region of interest. So like anything outside this region, we won't be predicting for it, and it won't go through the evaluator also. The black lines. So if you see on the right side, there are black lines alongside the colored line of a vehicle. So black line is basically the ground truth of that vehicle coming directly from Carla, and like the pink line here is the detection and tracking algorithms output. So I'll move back to the slide. Chromium. Yeah. So yes, so we were right now at here 62. And so the parameters that we use right now for detection, we had the confidence threshold as 80% and the IAU was set to be 0.5. And tracking the bird's eye view, we kept distance threshold to be 2 meters. And this is where we were getting those metrics for detection tracking algorithm. I'll show another edge case. We zoom this. So this is an edge case where we have like quite a dense scenario, and we're running a tracking pipeline here, like so both detection tracking pipeline here. So here you'll see some interesting things happening at the far boundary of the polygon because of homography transform, also because of boxes being like associated incorrectly to some other boxes, but like it works mostly fine at near the camera view. At far away, you'll find some peculiarities, like here at the here on this road in the left lane, you'll find this thing. So yeah, so like we're still achieving the metrics given a threshold. and the tracker seemed to be able to track vehicles fairly fine. Like that end, and also like here where there are occlusions, you'll find some like cases where it is not able to track perfectly.
I see. So that makes sense that occlusions would create problems. Like, I'm wondering what that triangle is in the upper central portion of, it's a pink triangle. It looks like that is the proposed track for the car. Is that right? Yeah, like if you go straight down, there's right there. Yeah.
Yeah. I feel this is basically tracker trying to predict, and we are plotting tracker's output, and then box might not be visible, but then the vehicle becomes visible after a time, and then we associate, and so the fused output position from tracker and this vehicle comes out to be like, so it basically realizes it is far, like it's a bit behind. So and that's why you see this this output here. So
basically due to the occlusion, the bounding box gets shorter, and then you somehow are able to predict that the car has started going behind. So that was a for the scope of improvement that we were talking about last time, that we might have to add like that a vehicle can only go in a certain direction. And so yeah, basically the bicycle model that we might have to add in order to make sure that it can only go where it is pointing.
Yeah.
So yeah.
Okay.
yeah, it changes in the motion model. So right now the pixels, so we are tracking the pixel space, and the motion model uses like constant velocity. Having like some kinematic model like may aid in improving this, but again, this is like a very dense scenario. We'll have to see like this fits to one of the cases that we'll actually encounter. But changing the motion model is definitely something we can try.
Yep.
I'll move to the simulation demonstration. I'll hand it over to Devil.
Going forward with the simulation demo, last time, as we saw, we added multiple agents in Carla simulator, and these agents are LBC agents, which we are using as our baseline behavioral model. And our aim was to get greater than 10 FPS for more than 3 actors. So so last time we were able to achieve around 9 to 11 frames per second with 3 concurrent agents. And the scenario was something like this, where 3 agents would follow a specific path and adhere to traffic rules and react to the traffic lights. So yeah, so this is a video of the last time's demo, and as you can see, after spawning 3 agents, we are achieving around 10.5 FPS on the left top left corner. Yeah, so one of the major feedback we got was how would this perform if we increase the number of vehicles, number of agents. So we did a study on while increasing the number of vehicles. So next up, we increased the number of vehicles to 10, and we can see the video right here. And I have added another debug view with which says with how many vehicles, what FPS is it achieving. So in the video, we can see I'm adding one vehicle at a time, and the number of vehicles are currently 5, and they are increasing, and we can see the server FPS going a bit down. So after the initialization is complete, the agent would start running, and we will see the FPS on real time, and on the bottom we will be able to see the aggregate or average FPS in these fields. So yeah, all the vehicles have been spawned now.
Now it's gone well, let's see, it's like 3.53, but it seemed like it jumped around a little bit, but you guys expected that above 3 vehicles, it was going to drop below 10 FPS, right?
Yes, yeah.
I guess the main question is whether it's a linear drop or it looks like it's kind of asymptotically approaching something. I don't know.
It is kind of asymptotic drop. So as you can see, all the agents are given start and end goal. As in when the end goal is reached, the actor gets destroyed, and so we will be able to see all the numbers filling up. Uh, uh, so I can just skip forward a bit. And as we can see, the number of vehicles currently are 6, and the the column with 6 vehicle FPS is currently uh, averaging its FPS number. So this is how we conducted this experiment, and at the end, I am skipping through. Um, Yeah, so these are our final results, where with 3 vehicles, we are getting around 10.61 FPS. But if we add more and more agents, these are the numbers. So I'll plot a graph. Yeah, so this is kind of a asymptotic drop where we can see uh, the FPS going down, but it's kind of getting stable at some value around here. So, so the next question is like, how can we improve this? So there are currently 2 approaches we can figure out. One is client-side development by introducing a simulator bridge. So all the agents currently are querying to build up a bird's eye view and to build up the relevant information for themselves to infer on the model. They are collecting the data from the server multiple times. So all the agents are querying the same data again and again. So introducing a simulator bridge would reduce this data gathering process, and it would greatly impact on the FPS. But this will also be uh, till a particular point. So the more general solution to this would be the server-side development, where you add the code for running the model in the simulator itself, and it would have the access to all the simulator parameters. This would be a very difficult task and a time-taking task. So depending upon the resources we have, time and the bandwidth, we would be choosing one of these and improving the scenario. So I will also demo one more scenario where I will run 3 agents, uh, which are LBC agents and default autopilot agents, and we will see how they react with the server. So I am starting up server view. So these red trucks are LBC agents, and I'll be spawning 3 agents. And I'll be adding more vehicles around the city. So yeah, as you can see, the other vehicles are reacting to the environment. Also, the Kala LBC agents also are reacting to the environment. Here, uh, the truck is stopped because it sees the another car waiting on the traffic light.
I do have a
yeah.
question about this in general. What is the difference between the car in terms of computational requirements between the cars that Carla uses its autopilot on and the ones that you guys are adding? Because you can do 43 vehicles, 42 vehicles here without bringing it to its knees. So is Carla doing something much simpler with their control?
Yeah, so currently the Carla is using rule-based agents where it just has to specify that uh, if this happens, it should perform this. So the model is a very simplified version of what we have. Also, all the code for this has been written in the server side.
Yeah.
Yeah, so that's the major difference.
Okay, so that's one of the solutions that you proposed on the earlier slide,
Yeah,
to go on the
yeah,
server side, and then you can probably speed your stuff up quite a bit that way.
yes, yes.
Okay.
So I'll switch over to the slides now. Yeah. Harsh would take care of it.
Yeah. I'll talk about the. So this is based on the SVD feedback that we got. So of all the algorithms, we. One second. So we just evaluated all algorithms on like different scenarios, and for detection, so we had a test data set that we evaluated our algorithm on and so we set different confidence threshold and we check the precision and recall values. So IU used for like the IU overlap used was like 0.5 in this entire experiment, and so you see so the IU that the confidence threshold that we're going to use is 80%, and the precision recall values we are getting is 97, 90, and like in the rest of the confidence values also we are getting much higher number. 80 seems to be like reasonable, and so this basically is satisfying the third and fourth mandatory performance requirement. For tracking, we as I said, we used 20 pixels in the bird's eye view as a threshold. Given this threshold, we are evaluating mod A and mod P numbers, which basically give how correct is the association and what is the deviation related to the threshold of the vehicles. So we, for this experiment involved running the capturing data from different traffic lights and running a tracking algorithm, like both track detection then pass to the tracking algorithm, and so on average we get like 80 and 67 as the numbers. So this satisfies our fifth mandatory performance requirement. Also, yeah, this was done on varied traffic densities as well. And so like on denser traffic, you do find mod P to go down. For simulation, they will just mention. So the FPS we are getting right now with increase in number of vehicles right now looks like this. Yeah, that's it. We are open for questions.
Good. Dimi and TAs, do you guys have questions? We got about 2 minutes.
Not a question, but I appreciate your last few slides where you summarized. That's very, very important, right? Because that shows, where you stand in relation to validation of your key requirements, right? And hopefully you will use that information as well to see if there is another maybe area where the requirements where you maybe want to get to, right? Based on precision values that you see, where maybe you draw, and where that may have an impact on real systems as well. So no question. Good job.
Yeah. Thank you.
No questions from me.
Okay. Yeah, I think that's good. I guess we only have about 45 seconds left. Well, I think you guys have, as Dimi said, a good grasp now on what the performance is and all. I guess just looking forward, maybe just a comment, be good to know where you need to be in terms of your MOTA, MOT-P, recall precision, et cetera. But I think that'll come into greater focus as you actually start doing specific use cases.
Yeah.
Okay, sounds good. I think we better go to the next team, but thanks a lot, you guys.
Thank you so much.
Thank you.
Thank you.
See ya. All right, we're ready for team F.
All right. Can everyone hear me?
Yep.
All right.